Welcome to Goobertown Hobbies. My name is Brent. Today we are going to talk about two-part epoxies and how they work. So we'll talk about what each of those parts is and how they do what they do. Now obviously there are a lot of different two-part epoxies out there. Everything from this Parks Glaze resin to Loctite adhesive to these molding putties like Green Stuff and Milliput. Of course, there are glues and putties on the market that don't need to be mixed with anything for them to work, but these two-part epoxies have a lot of great qualities. Once they're cured, they're strong and durable. Most of us have the understanding that epoxies mean serious business. Here I am using epoxy to glue down some very strong magnets to the underside of some bases for figurines. Those magnets are going to try to break that adhesive and escape. But epoxy is serious business, and those magnets aren't going anywhere. The tip on this double syringe mixes part A with part B, and I've got to work fast before that mixing tip becomes permanently clogged. As epoxy hardens, the chemical reaction that's occurring doesn't involve the evaporation of water or any other solvent. It's not actually drying in the same way that glues and putties dry. Since nothing is evaporating, this stuff doesn't shrink as it hardens. That makes it great for molding and sculpting. Here I am sculpting some cobblestones onto the top of one of those bases. It's workable for a few hours, and when I come back the next day, it looks exactly the same, but it's hard and super durable. Okay, it's time to talk about how this stuff actually works. We're going to talk about the real chemistry, but I promise you don't need to be a chemist to understand this. Now, some of the manufacturers give us some hints as to what's going on. So for Super Glaze here, they tell us that part A is the epoxy resin and part B is the activator, whatever that means. For other products, Kneadatite, Green Stuff, they tell you you've got yellow and blue in here, which is maybe less useful. But I assure you that across all of these products, it's essentially the same chemistry going on in all of them. The word epoxy comes from epoxide. Now, in chemistry, this is an epoxide. We have two carbon atoms and one oxygen atom all bound together in the shape of a triangle. Now, if you can understand simple shapes, I assure you, you're ready to learn about this reaction. Okay, so this isn't actually a molecule in itself. The simplest epoxide is this. This is ethylene oxide. And the difference is that I have added 2 hydrogen atoms to each carbon atom. Now, carbon as an element tends to make 4 bonds. So this carbon here is making a bond to the other carbon in the ring, the oxygen in the ring, and then 2 hydrogen atoms, so that is making a total of 4 bonds. And the oxygen atom, oxygen tends to make 2 bonds, and so it is happy as it is making a bond to each of those carbons. Okay, so this is the simplest epoxide molecule there is. Of course, we're going to be dealing with something larger, so we can replace one or more of those hydrogen atoms with a bond to a much larger molecule. And so, what we're actually working with in this reaction in all these products is this. This is bisphenol A diglycidyl ether, and you can see that there is an epoxide group over here and an epoxide group over here. Now, most of the rest of this molecule is just kind of filler. I mean, it's sturdy and durable and resistant, but mostly it's just there to make up the bulk of the molecule. The actual reactive bits are the epoxide over here and the epoxide over here. Let's take a closer look at this epoxide group. You can see that the plastic sticks from this model kit are bent. This little ring was physically difficult for me to make, and it's kind of spring-loaded. It really wants to pop open. Chemistry model kits represent some things better than others, and the fact that this ring is barely sticking together is actually a pretty good representation. This is all about shapes. So carbon likes to make 4 bonds, and when it's making 4 bonds to 4 different atoms, we end up with this tetrahedron shape. So here we have methane just as an example, carbon at the center, hydrogen atoms bound to it. The hydrogen atoms are equally spaced as far away from each other as they can be, and the result is that the angle between any two bonds in this tetrahedron is 109.5 degrees. So, in my model kit, there are 4 holes drilled into each ball, and they're drilled 109.5 degrees away from each other. Now, in nature, 5-membered rings are quite common, and the reason for that is if we have a regular pentagon, the interior angles should be 108 degrees, which is pretty close to 109.5, so it was easy for me to make this model, everything fit together nicely, and indeed the actual molecule in nature is quite stable and quite common. 6-membered rings are also quite common in nature. This distorts a little bit out of the plane to make the angles work out, but again, there's no strain here, everything fits together quite nicely. But if we start going down in size, say 4-membered ring, a square should have 90-degree angles, and that's starting to get kind of far away from 109.5, so you can see there's a little tension in this model kit. It's a little harder to jam these plastic bits together, but when we get down to epoxide size, when we get down to this triangle here, we're talking 60 degrees on average for these angles, and 60 degrees is quite a ways away from 109.5, and so that's why we end up with this shape that really wants to pop open. You can see that I've kind of bent my sticks for this model kit here, but it really does not want to adopt this triangle shape. So this epoxide is very reactive, and the reason for that reactivity is pretty much entirely because of its shape. It does not want to be a triangle. So when we start with a molecule that has that epoxide triangle, that's going to be a reactive site, and when we mix it with an activator, we're going to be able to get a reaction to occur. It's literally the shape of the epoxide group that makes it reactive. How cool is that? Carbon-oxygen single bonds are often strong and stable, but in this case there's an energetic drive to break one of those bonds to open that ring and relieve all that angle strain. So epoxides are real. You can synthesize them, you can bottle them up and store them on your shelf at room temperature for a while, but that being said, they're still these tightly coiled triangles that are spring-loaded and ready to react. So if you give them an excuse, an activator, they will react. Now, let's figure out what this activator is and then put these two parts together and see what happens. When I'm trying to figure out how a chemical product works, I look at the safety data sheets. Companies are required to disclose what potentially dangerous chemicals are in their product. It's one way to sort of get an ingredients list from a manufacturer. They aren't required to list benign chemicals, and they can be a bit cagey to make it hard to reverse engineer their stuff, but a lot of times we can puzzle out what's going on. So as sort of a funny example, green stuff here, the safety sheet tells us that talc is the only dangerous ingredient. Now, I'm pretty sure that there's epoxy resin and activator and dyes in here, but talc is the only thing we gotta be worried about. And, obviously that's not very useful, but luckily some of the other manufacturers are more forthcoming in their ingredients list, and I'll prove in just a moment here that this really is the same stuff as everything else on the table. And most of these for part A are indeed this badge molecule with maybe a little bit of solvent, but the part B, the activators, are a more complex mix. There can be solvent and plasticizer and other stuff in there, including more than one type of activator molecule. And there were differences between the activators for these products, partially because they're shooting for different properties, both the working properties of the two-part mixture and in the properties of the final solid. It does make sense that the putties contain clay and talc, but the glaze doesn't. This is the blend of stuff in the Parks Glaze activator bottle. So probably the most important and useful molecule for understanding this reaction is this triamine right here. Now, mostly this is just a big, durable molecule that's going to end up being part of the polymer matrix that we're forming in this reaction. But the actual important bits are the nitrogen atoms here in green, and here, and here. So nitrogen atoms tend to make 3 bonds. So this nitrogen atom is bound to carbon and 2 hydrogen atoms. And then in kind of the 4th spot of the tetrahedron, there's a lone pair of electrons. That pair of electrons is what's going to bond to the epoxide from part A and cause that ring to pop open. Nitrogen is an electronegative element, which means it can pull electron density towards it from the atoms it's bonded to. The overall molecule has a neutral charge, but there's a partial negative charge sitting on that nitrogen atom. Oxygen is also electronegative. In the epoxide, the oxygen atom has a slight negative charge, and the 2 carbon atoms have a slight positive charge. Okay, so partial negative charge on the nitrogen, partial positive charge on a carbon, combined with this strained 3-membered ring that wants to react and pop open. All of this is going to work together to make this reaction happen. So we mix in part A with part B, and molecules are moving around, bumping into things, bouncing off of things. But if they collide at exactly the right angle, this reaction is gonna happen. Oh, it's a bit more likely for the nitrogen to collide with the more exposed carbon of the epoxide, and that's all I'm gonna say about regiochemistry. Okay, the collision happens. The nitrogen from the activator amine is next to an epoxide carbon. I will now draw electron-pushing arrows to indicate the movement of pairs of electrons. The lone pair of electrons from the nitrogen is nucleophilic and starts to make a bond with the carbon. Because of the slight positive charge and the energetics of the epoxide, that carbon atom is able to act as an electrophile. Carbon makes 4 bonds, not 5, so as that nitrogen-carbon bond is formed, the carbon-oxygen bond is breaking. This is indicated by the bonding pair of electrons moving to reside solely on the oxygen atom. Making that new nitrogen-carbon bond joins 2 big molecules into an even bigger molecule, and breaking that carbon-oxygen bond busts open that strained epoxide ring, making the reaction energetically favorable. The important bonds have been made and broken, but the purist will note that we now have a nitrogen making 4 bonds and oxygen only making 1. No problem. Moving an H+ from the nitrogen to the oxygen cleans that right up. Here's the product. It's a bigger molecule, and that new bond is way more stable than that epoxide group was. On one end, we still have the second epoxide group, and that can react with other amines in solution. And our activator molecule still has 2 nucleophilic amines ready to react with some more epoxides. As the reaction continues, more and more of these molecules bond together, eventually resulting in a massive cross-linked polymer. The starting mixture of smaller molecules was a fluid, but as the molecules bind into larger and larger structures, it all ends up as a permanent solid. This stuff is chemically and physically durable. This stuff is serious business, and it's why we're willing to put up with the hassle of 2-part epoxies. Okay, let's talk about ratios. So the instructions tell us to mix 1:1 of part A and part B. And that's kind of interesting because in the example chemistry I just showed, each molecule of badge can make 2 bonds to activator. Each molecule of activator can make 3 bonds to badge. And added to all that, they have different densities and molecular weights. But in theory, the exact ingredients of part B have been tweaked so that these ratios all work out. Anyway, I decided to see how important it was to get those ratios correct. What I'm doing here is mixing some epoxies at the wrong ratio. Everything from 1 part A and 9 parts B to 9 parts A and 1 part B. Partially, this is because I'm curious how important it is to measure precisely when using epoxy. And, from a chemistry standpoint, there are conditions under which part A could polymerize with itself. Once an epoxide ring pops open, that negatively charged oxygen could act as a nucleophile and react with another epoxide, potentially leading to a chain reaction. I was interested to see if part A mixed with just a little bit of activator could get things started and give us a solid polymer. The answer in this case is no, but let's take a look at the results. After a full 48 hours of cure time, I took a look at my samples to see whether or not they gave a solid. The 50-50 mix gave a nice durable solid, as expected. The mixtures that were either mostly Part A or mostly Part B ended up being thick gels. It seems like too much epoxy worked a little better than too much activator, but not by much. Both of the 60-40 mixtures yielded solids. They were noticeably different from the correct 50-50 mixture, and who knows whether or not they've got any strength, but at least they are solid. In the future, I'm still gonna aim for 50-50 mixtures, but I'm not gonna stress too much over the fine measurements. I've got one more experiment here, and this is really just to scratch an itch. Now, I told you earlier that the STS for this green stuff is less than satisfactory. It just tells us that this contains talc. I'm pretty sure that this is an epoxy putty, but it was really bothering me that I didn't know for 100% positive. So I designed a simple test to check this out. Milliput does tell us that it contains badge epoxy resin in one tube and an amine nucleophile as an activator in the other. So I mixed up all 4 combinations of the 2 parts from Milliput and the 2 parts from green stuff. In theory, 2 of these should harden up and 2 of these won't. And yep, that's what happened. I have 2 pebbles here. The activator for green stuff cured the epoxy from Milliput, the activator for Milliput cured the epoxy from green stuff, and I ended up with solids. On the other hand, when I mixed the 2 activators together and the 2 epoxies together, we still have putties for both of those. Now, I'm sure there were probably easier ways to confirm that yes, indeed, green stuff is a 2-part epoxy, particularly maybe if I was better at searching for patents or something, but this way worked. It was easy, it was straightforward, and it was satisfying. Okay, I guess that's all I really wanted to say for today. The core take-home message here, epoxies get their name from epoxides, and those epoxide groups are reactive and ready to form a new bond. Now, between all these different products, the exact ingredients vary a little bit, but that core epoxide chemistry is the same for all of them. Now, I really like making this type of video. I find that it satisfies my curiosity, and it's just always good to get to know our hobby supplies a little bit better. So I'm going to keep making these. Let me know if you have any requests. Like, subscribe, all that good stuff, and thanks so much for watching.